So, Mohtasib, you are ready now?
Yes, yes.
Good. Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullah, everybody. I wish everybody is in a good health, and also I would like to thank everyone who is joining us today as a part of our series of webinars. As we speak today, this is our part number 3 of our webinar, which is titled Mitigating Poor Power Quality Issues. Before I start, I would like to introduce myself. I'm Khalid Al-Milham. I'm the Business Development Director on Suhaimi Design. And we would like to just give a brief about Suhaimi Design, which is a multidisciplinary organization since 1974. We have 2 divisions as we speak. A division which focusing in HVAC design, district cooling, and industrial process cooling since 2008. And also we have another division which is ProtecCooling, a division that focuses on improving energy efficiency for commercial and industrial sectors, which started in 2016. Before I start, also I would like to introduce our presenter, Mohammed Mohtasib. He is the manager of the ProtecEnergy division in Suhaimi Design, and he holds a bachelor degree in electrical engineering, and he has 4 certification, international certification, which is CEM, CA, CMVP, and ISO 50001. Mohtasib, he has 19 years of experience in energy management, power quality, system design, also an implementing of energy efficiency projects and power quality projects. He has conducted 600 energy audits in India, South East Asia, Europe, and Middle East. And also he conducted more than 25 projects implementing energy efficiency financing, and also experience in demand aggregation and implementation, utility, and customer level power quality projects. Also, he conducted the various training programs for utilities and industries on power quality and reactive power management. Also, he developed an application notes for power quality in IT, ITES industry, power quality in textile industry. And also he is a part of a committee of developing of US GPC rating system, performance excellence in electricity renewable peer. Now I would like to hand over the mic to Mohammed Mohtasib to present today's webinar.
Assalamu alaikum. Thanks a lot, Khalid, for the introduction. Now, today, as Khalid mentioned, this is our third webinar in a series of 3-part webinar series, which we had focused on power quality. And earlier that, we had an webinar on managing power factor. So in earlier 2, we had focused on in power quality, the basics of power quality and how it impacts financially. The second was more on harmonics and understanding the IEEE standard. Now the third, this is going to be more on how to mitigate, what methodology we have to follow for mitigating power quality issues, which are the different solutions available for some of the power quality issues. Then some of the case studies, and we'll be focusing more on question and answers. Now, we cannot cover all the mitigation techniques for all power quality issues which are present. So, we'll be focusing on a few limited power quality issues with few limited solutions. Now, the most important thing when we look into power quality is the methodology what we follow for mitigation to mitigate poor power quality issues. So, this is one of the most important thing what methodology has been followed. Now, in order to for PQ methodology, we need to understand some of the rules. First is like electricity is a raw material for any production, any service industry, whether it is a hospitality, uh, hotel, hospital industry, manufacturing industry, process industry. Electricity is a raw material. Like all the raw material, need to turns to its cost. So, electricity as a raw material, and like we all understand that other raw material, if the quality is not good, the final product is not going to be good. So the same is with electricity. Then refer IEEE definition for power quality, which says that the concept of powering an equipment in a manner that is suitable to the operation of that particular equipment. So here IEEE talks about not just about the electrical parameter, but it also talks about the equipment. So we need to take into consideration both, that is the electrical quality as well as the equipment, to come to a conclusion whether we need to it is a good power quality or bad power quality. Now, rule number 3, which is very important, is like analyze, analyze, analyze. We need to do a lot of analyzation, study, and different need to see different scenarios to come to a solution of poor power quality. So we need to find through analyzation what is the source of poor power quality, how it is being impacted, what are the financial impact, what safety concerns it may face in future. So we need to do a lot of analyzation for any PQ method, mitigation methodology. And rule 4 is the knowledge is one of the most important thing when solving PQ problem, not the technology. Now, application of technology for the right problem at the right place, it is very important. That there are a lot of technologies which are available for PQ mitigation, that is, which can be used for mitigation of poor power quality. But the application of that particular one technology for a particular power quality issue has to be selected properly. So it is very important that we should have a very good knowledge of power quality, not only about the power quality but also the basics of electrical engineering. So that will help a lot in mitigating power quality issues. Now, mitigation techniques for power quality issues. So first we'll be looking at voltage sag. Now, voltage sag are basically under voltage phenomena where the voltage value goes below zero point 0.9 pu, 90% below the 90% value of your rated voltage, and it lasts less than 1 minute. So one of the most important thing is that we need to differentiate whether it is a voltage sag or is it a under voltage, because sag and under voltage, these are two different things. They are differentiated by the time. So if it is the event is for less than 1 minute, then it will be a sag. If it is more than 1 minute, then it will be classified as under voltage. And the solutions for both of these things could be different. So we need to confirm whether the issue is related to voltage sag or under voltage. Then we need to confirm the event characteristics. What is the intensity? What is the time duration? That is, if the voltage is falling to 50%, 40% of its rated value, or 60% of its rated value. and for how much time, that is how much cycles, how many seconds it is lasting. So this is another very important characteristics that we need to look into, because it will help us in identifying the most appropriate solution. So based on the intensity and time duration, so there would be certain sites, if you can see over here, so which is like no damage region. So this is a CBEMA or ITIC curve. Which defines that impact of voltage quality issues, mainly under voltages and over voltages, sag, swells, under voltage, over voltages on electronic equipments. So no damage region. Then we have the prohibited region where we cannot apply, we cannot go in this region. That means there is the voltage level, and then we have the time. Then we have no interruptions region, and where there would be interruptions. So here in the no damage region, there will not be any physical damage, but there would be slipping of the equipments. Then for not only for the SAG, but for any power quality issue, uh, we need to identify the source of SAG. Whether it is within the plant boundary, within the building boundary, or it is outside the boundary of your facility. If it is within the facility, so we can have a different set of solutions. Our methodology for solving the issue would be totally different. If the issue is coming outside the boundary, then our methodology could be totally different. Then again, if the SAG is balanced in nature or unbalanced, because depending on the SAG, whether it is same in all three phases or there is an unbalancing, so then also the solution can differ. So we need to consider all these aspects. Not only all these aspects, depending on site to site, there could be many more aspects, but these will be the general guidelines what can be considered for SAG mitigation. Then if the SAGs are within the bond, then can SAG be limited at the source? Now, any power quality issue, we need to focus on the source. Now, power quality issues can be damaging some equipment in the plant, which could be at a far off location from the source of power quality issue. So, we need to see whether we can eliminate the power quality issue at the source itself, not at the protecting the equipment from the poor power quality. So our first objective should be, can SAG be eliminated at the source? Now, available mitigation technologies on the load side to prevent damages through SAG, we can go for UPS, some UPS with inline batteries, depending on what load you want to protect. So UPS, that is one of the common solution for protection against SAG. Then CVTs, that is also like a constant voltage transformer. So that will also depend on the type of load you are using. If there are a lot of fluctuations, so then we can go for like CVTs. And then we have like solid state sag correction devices. So these are basically static devices where uh, in some cases like capacitors are used as a energy storage to give desired voltage when there is a sag. In some cases, batteries can be used. So, but the most important thing is that how fast the switching mechanism is there for these solid state correction devices, because it should detect the sag at an early stage and should prevent it, should compensate by giving additional energy. So these are also one of a good solution which can be applied on the load side, but it all depends on what kind of load and which would be the best suitable technology. Then on the source side, now the SAGs we have seen in the last webinar that the SAGs are generated basically the starting of the large loads. If we have loose connections, if we have undersized cables, transformers, or conductors in the distribution network. So in order to correct the SAG on the source side, what we need to do is we can go for soft starters for large loads. We are not saying VFDs because what we have seen a lot of industry they are using VFDs as a soft starter, which is not a right approach because VFDs uh, their application is mainly designed to change the frequency of the incoming supply load to meet the changing load requirement. So it will change the speed of the pump, fan, blower. But what we have seen is that a lot of industries they're using VFDs as a soft starter, only for the starting of the motor. Now, it has a couple of disadvantages. One disadvantage is like you can go for additional investment. The investment will be higher in case of VFD as compared with soft starter. The second part is VFD will be having its own energy consumption. So if you are operating at like 60 hertz with VFD, so it will be consuming at least 2-3% more energy of the total energy consumption. Then the harmonics generated by the VFD. So that is another issue. So if it is only for the starting, or go for the soft starter, then identify any loose connections in the network. So if there is in any in-fresh current, so due to loose connections, the voltage drop could be higher, converting that inner current into a higher voltage drop and causing a sag into the distribution network. Then if the cables are undersized, then again they can cause sags in the distribution network. So we need to look at these aspects first before going for the load side mitigation techniques. Now this is a case study. It was done for a process industry, so a continuous process industry. So they had issue of tripping of VFD on one of the process motor. And each tripping there was a loss of like productivity for about 30 minutes. So there was a financial loss associated with these trippings. And monthly they used to have about 3 to 4 tripping. So there was a considerable financial loss, and not only just tripping, not only the productivity loss, but the loss of the material which was in the process. So there was a financial loss, and plant has considered that they will install a UPS for these critical load, that is a VFD. So VFD will be fed by UPS, and the investment was about 600,000 or 0.6 million Saudi Riyal. Now we got involved into that to first the objective of the client was to again validate what should be the size of the UPS system. So we again like studied, we did a few measurements in the plant at the critical points, and we identified the sag. So there is like a constant voltage supply, and there is a sag event, and again it came back to normal. And the sag event, it was about like 5 millisecond. It was the duration of the sag events, and 40%. So 40% means the voltage was dropping up to the 40% level of its rated voltage, and it was sufficient to trip the VFD. Now, there was nothing wrong with the solution because this solution would have worked very fine with this kind of sags. So UPS would have taken care of these uh, sags. But what we suggested that if the plant can give us some time, so we can identify a better solution. So we did a further detailed study of the facility. We identified the source of sag as an air compressor motor. So there was an air compressor in the plant, which was not operating on load unload mechanism. It was operating on on off whenever needed, and the requirement was also not on a continuous basis. So what we recommended is we changed the feeder of this air compressor, modified the compressor sequence operation. For this, the investment was 25,000 Saudi Riyal for the client. So we have reduced their investment, which was earlier about 0.6 million, to about 25,000 Saudi Riyal. So the result was that the SAG reduced to 82 to 85% for 5 milliseconds. So that means like earlier, which was up to like 40%, has come down to 82 to 85%, which can be easily be handled by VFDs. So benefits is like they have avoidance of productivity loss, and beta analysis has resulted in them in less investment in the solution. That is the solution what they have earlier adopted, and what solution has been given. So which was much better. Then transients. So we have seen the definition of the transients, how they occur in last webinars. Again, we need to confirm whether the issue is related to transient. So before going for like any mitigation techniques, we have to be sure that whether that issue what we are facing in the facility is due to transient, voltage dip, voltage sag, under voltage, or harmonics or unbalanced. So we need to be very sure that the issue is related to transient. Then we need to confirm transient characteristics, that is what is the type, its intensity, time duration, and decay time. Identify source of transient, whether it is within the boundary or outside the boundary. So the source of transients are mainly your capacitor bank, switching devices, or lightning. Now for lightning, we can't do anything. But the other in-house sources, that is like mainly capacitor banks, so we can work on that. Then identify if the sag is impulse or oscillating in nature. So your solution will change accordingly. The available mitigation techniques, one of the most common and proven technology is SPDs, that is surge protecting devices. But while selecting an SPD, the life of SPD is very short as compared to other electrical equipments. So we need to be very careful while selecting the life of the SPDs. And if the SPD has failed, we will not even come to know. So we need to like check for the life of the SPDs. Then what is the terminal or connector length and bends. And we need to understand the operation of the SPDs and selection of SPD. So we can have a detailed session only on SPDs sometime later. Then on the source side, like as we mentioned, capacitors are one of the major source of transients. So we need to ensure that the switching of the capacitor banks is proper. Then what is the rating of the capacitor banks that has been installed, and what is the time delay that has been given. So these factors are very important than while we are installing a capacitor bank. Then ensure that you go for synchronized switching. So synchronized switching ensures that there are no or negligible transients in the system. Now we'll see in brief what is synchronized switching as well in this case study. So in manufacturing industry, here they have complained frequent failures of electronic cards. So there was a manufacturing industry, and electronic cards in their like CNC machines, other machining equipments, and critical testing equipment they were facing, and loss in productivity and replace and the cost for replacement of these cards. So we did an analysis. So transients were identified. Then we checked the historical events, historical like failures of cards since when they have started. So same some date was mentioned, month was mentioned, and the same month and particular year they had installed capacitor banks. So basically, the failures started after installation of a power factor correction capacitors in the facility, and the switching was contactor based. Now, when we have a contactor-based switching for automatic power factor correction capacitor banks, so what it does, the contactor-based switching, it doesn't know at what point of the waveform it is switching on the capacitor banks or switching off the capacitor banks. So if the and every time whenever there will be a switching, there will be transients in the system. So depending on at what point the switching is occurring, there will be that will decide what is the intensity of the transients. So let's say the switching happens at 30 degrees. So if this is the would be the probable like magnitude of the transients. Now instead of that, if the switching happens at the peak of the waveform, then in that case, what will happen? Our transient will be of very high magnitude. We'll be seeing transients of very high magnitude because we are doing the switching at the peak of the waveform. Now, in the synchronized switching, so what we basically do, it is basically thyristor based or IGBT based switching, where the switching is ensured at the zero crossing. So switching will be done at this point of the waveform. Now, at this point, since there is no voltage at the zero crossing, there will be no transients or very minimum transients generated into the system. So which can be handled by the system very easily. So what we did, we asked the plant team to change the switching mechanism to thyristor-based switching, so which they did, and modified the steps of switching and time delays. So after that, the issue was solved. Then harmonics, as we have seen, there are multiple integer multiples of different frequencies. So a lot of solutions available for mitigation of harmonics. So as compared with other power quality issues, harmonics are basically a steady state phenomena. So that means that harmonics are going to be present into the system on a 24/7 basis. So unlike like transients or voltage spike, we don't know at what time they will occur and go. But harmonics, they are going to be present everywhere. So it makes the life easy as well as difficult. Easy means we can measure it anytime, and we need to live with it always. So first thing, whenever we are dealing with harmonics, the first thing what we need to do is we have to verify whether we are under IEEE 519 limits. We need to comply with the legal obligations. So IEEE 519 2014, that is the legal obligation that we need to follow. And this we have seen in detail in the last webinar. Now, being complied with IEEE 519, it doesn't mean that you will not have any issue with the harmonics in your facility. Now, IEEE 519, it only limits the ill effect of your harmonics onto the utility, the distribution company, or to the neighboring plant or other plant. It doesn't ensure that you will not have any issue related to harmonics within your facility. So these are two different objectives. So like IEEE 519, it will only comply with the legal obligations, which will ensure that you are not disturbing or polluting the other consumers or utility. Now, when doing study for IEEE 519 also, you have to also be focused on imported harmonics. Now, harmonics not necessary at your meter or at the point of common coupling will be only your harmonics. There will be harmonics which will be coming from plant. Your chemical industry and your is a steel plant which is having a lot of induction furnaces. Now, there are very much possibility that those harmonics will be reflected on your facility. So, how you are going to differentiate those harmonics, that is imported harmonics, that becomes an important factor while studying for IEEE 519. So, we have to, you are not responsible for the harmonics generated by someone else, and you should not be responsible for that. But you can say that only when you know that you are being polluted by someone else. So it is very important that you should know uh, whether the harmonics which are seen at your point of coupling are your own harmonics or are being imported from somewhere else. Then you need to evaluate harmonics within your boundary, that whatever is your plant boundary, you need to evaluate the harmonics. So what you need to do is based on the SLD, based on your non-linear load into the system, different impedance of the network, you need to evaluate the harmonics within the facility. Then we need to evaluate the impact of harmonics on the system, because harmonics are going to be there. So if there is no negative impact of the harmonics, there is no need to mitigate or install any filters or do anything about the harmonics. You need to mitigate the harmonics only when there is a negative impact of the harmonics. So for this, one thing is that you should be knowing that there is a negative impact of the harmonics. Most of the time it happens that there are negative impacts, but the plant people or the utility people, they don't know it is due to harmonics. So uh, we need to evaluate the harmonics, and we need to evaluate whether there is an impact of harmonics on the system or not. If there is no impact, we don't need to go for any solution. But if there is an impact based on uh, productivity loss, tripping, failure of equipment, or a safety impact, so we need to go for mitigation. So mitigation techniques, the first thing what we need to look into harmonics at the design stage. So at the design stage, always go for low harmonic generating technologies. Now, with energy efficiency taking place, now everyone is going for energy efficiency. It is going to be one of the important aspect of your like our day-to-day professional life for all the engineers. So we are selecting the equipments for energy efficiency. A lot of people going for LED lights. A lot of people are going for VFDs to reduce the energy consumption. Now, all these equipments, they will be generating harmonics. So we are not saying that don't go for LED lights or don't install VFDs, but we need to make sure that these equipments are also selected based on their harmonic generating capability. In the LED lights or LED, which is normally known as, what we have seen is the harmonics we have seen right from like 6% THD up to more than 160% THD. So that is the wide range of harmonics uh, available in the THD. So if you don't focus on the THD while purchasing an LED light, so you may end up with a lot of high neutral current into your system, as well as very high harmonics. Then at the design stage, you need to be ensure that your IEEE 519 limits at the PCC. Now, why we are talking about the design stage? Because at the design stage, any modification, it will need only some additional investment. You don't need to install a very new equipment to mitigate the issues. So one of the example is that at the design stage, you can go for like proper load distribution and phase shifting transformers. So any industry or building large or like hospitals or any establishment, they will be having a number of multiple transformers within the facility. Now, if a proper study has been done at the design stage and we know what are the harmonic generating equipments would be, what would be the percentage and what kind of harmonics will be generated through these equipments. So based on that, we can select like the phase shifting transformers, and they can cancel out a lot of fifth and seventh order harmonics. We can even go for multi-phase shifting transformers. So normally, which are not needed in the presently, but only 30-degree phase shifting transformers can reduce a lot of harmonics into the system at the design stage. Then go for higher size neutral conductor. So if you are having a building or a lot of electronic loads, go for a higher size neutral conductor, maybe double the size of the phase conductor. So that will reduce the ill effect of harmonics. It will be your operation will also be safe. Uh, and make sure the earthing is good, earthing and grounding, because this is one of the most important aspect when we are talking about any power quality issue. Earthing and grounding, it is the most important aspect of mitigating a power quality issue. Then for mitigation harmonics, we have n number of solutions depending on the type of harmonics or the order, magnitude, amplitude. We can go for different solutions. So for existing plant, we need to go for like a detailed study. We need to identify source of harmonics. So instead of mitigating the harmonics at the point of common coupling, it will be always better to mitigate them at the source. What is the source? So then we should know what is the order, sequence, and amplitude of the harmonics. Multiple solutions are available for mitigation of harmonics. Depending on harmonics and system characteristics, we need to select the most appropriate technology. So, and normally what we say, the best available technology may not be the most appropriate for you. So you could mitigate your harmonics with a very basic solution also. It is not necessary that you need to go for the most advanced technology always. So the mitigation technologies which are commonly used and available are tuned harmonic filters. So tuned harmonic filters, basically they will be also known as passive harmonic filters. So they will be creating a low impedance path for the harmonic order, what we need to filter out. So they are like comprised of our inductors, capacitors, and resistors. These are the components for an tuned harmonic filter, and they are designed based on the level of harmonics, the order of harmonics, their amplitude, and what is the impedance and short circuit capacity of your system. So this is like mainly like we have the inductance, capacitors, and resistors, nothing else. Very basic equipments, and they will be offering a low impedance path for a particular order of harmonics. So what we see from here, so we have for a particular frequency, the impedance is very low. If this is the normal impedance, so the impedance for that frequency is very minimum. So it will filter out those harmonic current will be passing through this filter. Other components or fundamental frequency component will not be passing through this filter. So that is how it works. It is low cost solution. Uh, Initial and operating both costs, that means like initial investment will also be less, operating cost will also be less for these equipments. They are reliable and easy to maintain. But designing of these filters is critical. We need very good expertise for designing of these filters. So although the initial cost, investment cost, its own energy consumption, Everything will be less, they are reliable, but we need experts, people to design these harmonic filters. Now we need to be differentiate these tuned harmonic filter with detuning. Detuning is not a filter like we have mentioned in the past also. Detuning is just a avoidance of amplification of harmonics. Detuning, we cannot call it as a filter. Then we have active harmonic filter, which are like solid state DSS. These are power harmonic. So they form one opposite to the harmonic current. So if you have a harmonic current of fifth order harmonics, so they will be generating a fifth order harmonics, these active harmonic filters, which will be 180 degrees opposite to your fifth order harmonics. So basically they will cancel out each other. So if this is the, let's say, harmonic current, so this will be generated by AHF. So these two, which are like in opposite phase of each other, they will be cancelling out each other. So even the active harmonic filters, that will be needing a system study, but that will not be as detailed for the tuned harmonic filter. Initial cost will be higher as compared to passive harmonic filter. Then operating cost also is quite high for active harmonic filter, because they will be consuming something about up to 3% or 4%, depending on what make, who is making that active harmonic filter uh, of its capacity. So you will be having an initial investment cost as well as the operating cost for these active harmonic filter. Then upon failure, these parts won't be available locally. It only has to be imported. So most of the only the OEMs can give, because these are like power electronic based. Mainly they will be IGBTs technologies. So that will be like need to import. So maintenance also will not be cost effective. We recommend the active harmonic filter only when there is a wide spectrum of harmonics are present into the system. So what we mean by wide spectrum, that is like you have the harmonics like third, fifth, seventh, 11th, 19th, 13th, up to let's say 25th order or 30th order with considerable amplitude. So then only we will be recommending active harmonic filter. Otherwise, any harmonics can be like you will be having maximum of like fifth, seventh, 11th, 13th, or few triplet harmonics, that is third, ninth, 15th order. So these can be easily filtered out using passive filters. Then we have a hybrid harmonic filters, which are like combination of multiple passive or active harmonic filters. So these also need a detailed system study. Cost will be in between active and passive, and application will be depending on the system. So none of the technology is bad. It purely depends on what is best for your system. Now we'll be looking at a very interesting case study for harmonics. We are not looking at any like application of active harmonic filter or passive harmonic filter, because that you can find a lot onto the net, and a lot of manufacturers also will give you a lot of case studies on active and passive harmonic filters. Now this is a case study. There were three steel plants. They were connected on a 22 kV line. Then all they decided to have a better voltage stability to higher voltage level, and they shifted to 33 kV line, which was supplied through a 25 MVA 132 by 33 kV utility substation transformer. So this is a simplified like SLD. So plant A, which was about 1 kilometer from the utility substation, was having a 10 megawatt load. Another which was like 6 kilometer plant B, 3.8 megawatt load. Plant C, 6 megawatt load with a 7 kilometer. The same transformer, it was also giving a load to a process plant, which was like having a load of about 3 megawatt and about 15 kilometer. Now, as soon as these steel plants were shifted on these transformer, this plant, process plant, they started to face a lot of issues. The frequency was deviating a lot. It was going up to like more than like 20-25% deviation in the frequency. They were not able to operate any of the electronic equipments, and they have to shut down the plant actually. So then the utility, even the plant B, they were facing a lot of shutdowns, almost 2 to 3 hours daily, which was a steel plant. So these two plants, they were facing issues. Now, the first thing what utility did, they shifted the process plant connection to another transformer. So now this transformer is supplying only to 3 steel plants. Utility transformer also, this transformer also started facing issues. So here the issues were like temperature and vibration issues. The temperature in the winters, when the ambient temperature was about 10-12 degrees Celsius, the transformer temperature was going in excess of 60 degrees Celsius. And vibration issues. So it was vibrating. You can actually feel the vibrations when we were standing near the transformer. So transformer, they cannot utilize more capacity, only 80% of the capacity. Now we did a few measurement at the utility transformer. So with different scenarios, when plant B and C were operating, all 3 plants were operating, plant C was operating, and only plant B was operating. So since utility was involved, we were we were able to ask the plant to shut down at a particular time, and they were complying with our instructions. And if you see the voltage harmonics were going up to like 12%, whereas the limit says it should be less than 5%. Then current harmonics, again, they were like very high current harmonics were being observed in the system. And at individual plant level, the interesting fact was that individual plant level, the VTHD were within limit. But at the utility transformer, they were going up to like 12% and not within the IEEE limits. Then plant A, TDD was 4.89%, which was under the limit. But they were exceeding 10th, 12th, and 23rd order harmonics. So there were even harmonics also in the system. B, again, it was 15.0, so which was exceeding by a lot. Higher order harmonics and even order harmonics were there. And plant C, again, TDD within limit, but only 23rd order harmonics, it was there, which was exceeding the limit. Now, in all these 3 plants, only plant B was having a harmonic filter. Still, the harmonics were exceeding the limits to a great extent at the plant B. Now we did a detailed study, measured in depth at different plants. So plant A and C, they were having capacitors all connected on the 33 kV side, whereas plant B was a tuned harmonic filter, also connected on the 33 kV side. Then we identified some issues in the rectifiers of the plant B furnaces. So we asked them to resolve that. So that solved the issues of even harmonics. So even harmonics were basically due to some issues in the rectifiers of the furnaces. Then higher order harmonics of this plant B, they were resonating with the capacitor banks of plant C and plant A. So we asked the plant A and C to detune the capacitor banks. So they did the detuning on the capacitor banks, and after that, these all harmonic issues were resolved. Then overheating of the transformer, that was resolved. Then utility reconnected that process industry to the same transformer and that is now operating without any issue. So if this detailed study was not done, so everyone would have blamed plant B, because it was by the measurement we could see that the only plant B is having very high order harmonics, which he wouldn't have been able to solve without the study of other plants simultaneously, which were affecting the entire system. The plant utility, they need to install a 50 MVA transformer instead of a 25 MVA transformer, depending on the K factor. And plant B, they had to stop the operation, or so these were the available options. So with a detailed study and analysis, a right problem was identified. So it is very important to identify what is the right problem first. So unless until we identify what is the right issue, we cannot go for a most appropriate solution. And after that, a cost-effective solution was implemented. So to sum up, a detailed analysis is very important for any power quality mitigation. So whenever you're going for a power quality mitigation, go for a detailed analysis. So analysis is key for a most cost effective solution. The solution could be few thousand reals as well. But for that, you need to go for a detailed analysis. Knowledge is more important than technologies. So you need to acquire knowledge or go for the people who has the knowledge in the subject. It will help you to identifying the most cost effective and technically reliable solution. So power quality mitigation, it is definitely going to help you in improving your productivity, reliability, quality, and profitability. So if you have any questions, now we'll take questions. Now we have a question. Sometimes customer ask to use diesel generator to run our chillers to provide temporary cooling in the building. We allowed, but during night times there was fluctuation in voltage for short period of time, which caused burning of controllers in our chiller. How can we avoid such situation, and how can we monitor and record the voltage fluctuation? Now, the issue is operating chillers on the diesel generators. Now, there could be different issues. First, we need to know whether your chillers are with VFD. If the chillers are with VFDs or any pumps are with VFD, then it is a totally different scenario operating the chillers with VFD on the uh, grid and on DG set. So if these chillers are with VFDs, there could be failure of contactor. It can generate a lot of harmonics, and it can burn out some of the contactors, and there you could face ill effect of the harmonics. Second thing is that if the load on the chillers is not proper, that can also cause under voltage. If some other loads are putting up on the DG set beyond its capacity, so it will the voltage will come down. So there could be multiple situations. So we can discuss this in detail. When installing a harmonic filter, what is the impact on power consumption? Now, passive harmonic filters, they will be consuming very little power as compared to active harmonic filter. So any equipment, any electrical equipment, even as static as a capacitor bank, they will have they will be having their own power consumption. Now, only thing what we need to look over here, which is having more power consumption. Active harmonic filters, they need more power consumption. They will be having more power consumption. So we need to select them if we really need them. Also, passive harmonic filter, if that is gone in terms of designing wrong, that can also consume a higher power consumption. But in general, active harmonic filters will be consuming more power as compared to passive of the same setting. Another question: how to measure observed transient wavelength? Transient wavelength that you need to install high-end power quality loggers, use power quality loggers to have the wavelength, transient wavelength. Another is how do you do the sizing of capacitor of a power factor controller, especially for the voltage setting. So voltage rating, the transformers, we need to see the impedance of the network first. Then what would be the voltage drop across the capacitor banks? Then what is going to be the actual voltage across the capacitor banks? What is the rated voltage of the capacitor bank? And based on the voltage is like square relationship, the voltage of the capacitor bank, operating voltage, will either degrade or upgrade the capacitor bank. So we need to consider what is the rated voltage of the capacitor bank and what is going to be the operating voltage of the capacitor bank. Then we have how we can avoid resonance in building due to filters. I understand. The resonance here, you're talking about electrical resonance. Now, the electrical resonance, if it is happening due to the filters. Filters, if the resonance is happening due to filters, there is something wrong because filters will not cause resonance in the building. So we only if you have plain capacitor banks, so that could cause resonance. Ideally, filters should not cause the resonance. If there is resonance is still happening, so maybe that is not properly tuned for the frequencies. Then we have another question. Can you please explain more about phase shifting uh, transformers, where exactly this can be used? Phase shifting transformers are basically delta Y or delta delta, where the internally the windings are phase shifted by about 30 degrees, 30 degrees or 35 based on the harmonic content what you want. So once the one transformer is having let's say a phase shift of 0 degrees, another transformer is having a phase shift of 30 degrees. So these two transformers will cancel out the fifth and seventh order harmonics based on their natural phase angle. Another is there certificate for the webinar attendance? No, it was only for the knowledge, not for the certificate. Then another question we have, in a commercial facilities, there is frequent failure of LED lights. Could this be a harmonic problem? How to pinpoint? Frequent failure of the LED lights, they are very susceptible to any deviation in voltages. So basically, the any transients. Now we need to look at what kind of failures it is happening. If the failure is in the driver part of the LED light, or it is slowly dimming away, or it is a sudden failure. So once we know what kind of the failures we have, uh, we cannot say that the failure is due to harmonics, because harmonics will not come back to the LED lights. Harmonics will always go to the upstream of the network, that is the grid. So harmonics will not be an issue which will be causing the failure of LED lights. We need to look into other issues like voltage transients or unbalance, in some phases, which may cause overheating of the entire system. Or we can also voltage transient could be one of the reason for failure of LED light. This is another very good question for the welding shop. Uh, in weld shop with high number of welders, there are issue with emphasizing and pulsing power surges. What is the best approach to plan such weld shops and also managing power surges? We did some of the projects for welding workshops or plants where there are a lot of welding loads. A Scott connected transformer could be one of the solution which will be solving the issues of unbalancing as well as the high peaks. So Scott connected transformer with shielding. So that could be one of the solution. Then can So for the electrical resonance in the building, confirm that it is electrical resonance. So because with harmonic, if you already have a harmonic filter, so we need to really see in detail that what is causing the resonance. Because if you would have said that only capacitor banks, that it could be the due to capacitor bank. But we need to see the system in detail to give any comment. Can we group a list of same characteristics equipment for designing passive filter, or it has to be for each one? Yeah, definitely we can group. We can most equipment in a plant or building will be having fifth or seventh order harmonics, so we can definitely group, and the passive filters can be installed at the distribution level as well. Then Uh, another question, we have three transformers with vector group DY11, DD0, DY5. What could be the reason for induction furnace load? Uh, need to, the question is not clear. If you can put a more clarity in the question, so maybe you can. How can I be an expert and certified in power quality audits? We need a deep training courses with certificate. Now, power quality, it will come with experience. Your basics has to be clear, and you need to spend a lot of time into the field to see the actual issues. What type of filters used with VFDs and when we can use? What is the acceptable limit for harmonics at VFD supply? Acceptable limit of harmonics at the VFD supply, that we are talking about voltage harmonics, not the current harmonics. If we are talking about supply, so anything which is up to 8% of VTHD, it should be acceptable to the VFDs. And generally, unless until the VFDs are causing a lot of harmonics into the system, we don't need to have the VFD at the filters at the VFD. It depends on the situation. If you have only one VFD, two VFD to the entire system, we can go for filter. But if we have a lot of VFDs, then we need to mitigate the ill effect of the harmonics onto the system. So in that case, a group of VFDs or at the bus where the VFDs are connected, There also we can have the harmonic filter, not necessary at the VFD, because that will make the system very complicated. It will have a lot of issues, as well as it will not be cost effective. Can harmonics generated by VFD damage the upstream power factor correction capacitors? Yes, of course, they can generate. We have seen cases where the capacitor banks have blasted, and unfortunately, one of my colleague in back in India has lost his life due to a like resonance in capacitor bank. Blast due to capacitor bank. So that you need to take it very seriously. So we are like through with the time. So I would like to thank you all for your time and attending the webinar. Any unanswered questions will be definitely come back with the answers. So Khalid, you would like to add something?
Yes, first of all, I would like to thank you, Muhtasib, for the formative presentation and knowledge sharing. I do appreciate everybody's participation, but also we would like to really add value to our, experience by sharing information among each other. Also, to save seriously nowadays, we need to look into our operation and to fine tune our also productivity and time losses within the operation. That will save a tremendous issue to the factory or the facility. In addition, we'll add into the whole thing, safety is first. Safety, by having a good knowledge and good engineering, I think will save good, portion of our safety and our personnel within the plant and so forth. I would like to thank everybody by sharing, also the questions with us. And we hope that we might can custom made type of presentation to each plant if needed by each factory if they require, where they can put their all concerns and they put all their issues in an email, and we can also collaborate with them in putting resolution to that specific concerns within that plant. With this, I thank everybody for attending, and hopefully we can form new webinars that will be advantageous to everybody. With this, I leave the last comment to our expert, Mohammed Mohtasib, please.
Yeah, thanks a lot, Khalid. So I also request if you have feel certain topics that would be helpful for you in power quality or energy efficiency. So if you can suggest, so we can organize those webinars as well. So with this, I would like to thank once again everyone. Be safe, be at home, and inshallah we'll see you soon again. Inshallah. Assalamu alaikum.
Alaikum assalam.